So far, we have talked about many sorting algorithms. The selection sort and bubble sort, insertion sort, quick sort, and merge sort. So now we have another sorting algorithms, heap sort. Okay. Heap sort is really simple. As long as you understand max heap, okay, then we are going to use the max heap. Okay, the idea is really simple. So let's take a look at these algorithms. Okay, first, sorting using a heap operations. Okay, that's a heap sort. So basically, in a simple way, let me explain how it works. So basically, given an unsorted list, insert all the elements into a max heap. Okay, so now we have a max heap. And as I said, when I explained the max heap, as I said, this max heap is not sorted, but in a sense, in a way, it is kind of sorted because the root node is always the maximum element. Okay, so we are gonna take advantage of this kind of property. Okay, so we have a max heap, and remember, to insert all the elements, it takes n log n. Now, when we're going to delete one element at a time, and actually we're going to delete the maximum element, which is the root node. Okay, so delete that root node, which is the largest one, and then adjust the max heap. And now next, delete the maximum element from that max heap, and then adjust, and keep doing this one until we have empty max heap. That's it. So by inserting all the elements into the max heap and deleting all the elements from the max heap, then we can sort. And the complexity is n log n for insertion and n log n for deletion. So in a big O notation, actually it is n log n algorithm, right? That's good. So total complexity is n log n, and as this figure explains, given this unsorted list, insert all the elements into the heap, into the max heap, and it takes n log n, and then now we have a max heap, and delete the largest element at a time. Okay, one by one. Then, after deleting the largest element, then we can have a sorted list. Okay, but we have a little trick. Instead of inserting all the elements one by one, we just insert all the elements into the complete binary tree first, and then we're going to adjust that tree to be a max heap. Okay, that's a slight difference, modification, but basic idea is quite simple. Insert all the elements into the max heap and delete all elements from the max heap. That's it. Okay, so this is an example of max heap. And to refresh your memory about max heap, let me explain what max heap is. The max heap is actually a complete binary tree. Okay, so we don't have anything like here. If we have one node here, then this is not complete binary tree. Okay, so we don't have this one, and this one is a max heap, so this one is larger than the other ones, and also this one is larger than the descendants. Okay, this one is larger than this one, this one is larger than this one. Okay, so this is a max heap. Now we are going to use this max heap to sort. Okay, first we are going to insert all the elements into the max heap, but as I said, we are not going to insert one element into the max heap and adjust, then next one and the next one. So instead of handling the element one by one, we're going to insert all the elements into the complete binary tree, and then we're going to adjust. Okay, so first step is to make a max heap from the unsorted list. So first, given this input list, we insert all the elements into the complete binary tree first. Okay, and in the complete binary tree, insertion is really simple. 26 goes to the root node, and then 5 and 77 and 1, 61, 11, 59. So it's quite simple, right? So it takes just n time complexity. Okay, so this is complete tree, and this is not maxib. 26 is smaller than 77, so this is not maxib yet. Now we are going to adjust an unsorted list to make a maxib. Okay, and then this one, basically we have two functions. Okay, so we have adjust function and the max heap sort function here. So in this heap sort function, we are going to call adjust function a couple of times. Okay, so let's follow this adjust function line by line. Okay, so first we have a list and the root node and the integer, the boundary of this tree. So the root is it could be a 1 or it could be 4. Okay, and n is the last element of the list. So it could, in this case, so in this example, right at the bottom of this slide, we have one example. So in this case, n could be 10, but sometimes if you want, n could be 9 or 8. So we'll see that later. Okay, then root could be 2, 1, 4. If root is 2, then we will focus on this subtree, and this subtree should be also a maxib 2. Okay, so with these parameters we define the range of this tree, okay, that we are interested in. And then first temp will get the root node. So let's say we are interested in this subtree. Okay, then the root is 2, and n is 10. Okay, then temp will have this node. Okay, and then the list root dot key will be root key. So root key will be 5. Okay, this 5. Okay, and then the child is actually 4, right? 2 times 2 is 4, and we are going into this while loop, and child is smaller than n, so n is 10 and child is 4. Definitely child is smaller than 10. Okay, so we are going into this loop, and child is less than n. If child is less than n, it means this node has a right child too. Okay, you see what I'm saying? If child is n, then the left child is the last element. Think about this one. If the root is 5 and child is 10, okay, then we don't have a right child. But if child is less than n, then we have right child. Okay, and we have a right child, and we are comparing the left child and the right child. And in this case, right child is larger. So child plus plus means now it corresponds to this case actually. The root is 2 and child is 4, but right child is larger than, the 61 is larger than 1. Okay, we are comparing the keys, not the index. Okay, so 61 is larger than 1. Okay, we get this case, and then child is now 5. Okay, and then next we are comparing the root key, which is 5, and we are comparing this root key to child's key, which is 61. So root key is if root key is larger than child key, okay, then we should stop there, because this one is larger than the children. Okay, then we will stop there. Okay, but this is not the case, so we are going into this else case, because the child key 61 is larger than 5. Okay, so we are going into this else statement, and list child divided by 2 will get list child. What is the list child divided by 2? Child is 5, and child divided by 2 is 2. This one is integer, this one is integer, so divided by 2 is actually 2.5, but since these two are integers, so the result is 2. So basically this one is actually indicating the parent. Okay, this one. So we are copying this one to this one. So in this case, we are not just copying the key, we are copying the key and the data and everything. We are copying the structure instance. Okay, so we are copying everything with the key 61 to here. So now this one is 61, but we are not overriding. We are overriding this one 5, but don't worry, we just copy this 5 into temp. So temp has 5 here. So when we overwrite this one, we don't lose that information. Okay, we have temp. Okay, next child is 10. Okay, so child was 5, now child is 10 by this one, and then we go back. Child is less than or equal to n. Okay, because child is 10 and n is 10, and we don't have right child. Okay, so we actually skip this part, and then we check root key 5, and the child's key is 19. So we are going into this else one more time, and list child will be copied to its parent. So 19 will be copied to 61, but don't worry, 61 is here already. Okay, so 19 is copied. Again, we copied the structure, not just key. Okay, the whole data will be copied to this one. And then next, child is 20, and when we go back to this statement, and the child is 20 and n is 10, so we quit. And finally, we copy this temp to child divided by 2. Child is 20, so child divided by 2 is 10. So temp will be copied to this node. Okay, so after these functions, then we have, let me rewrite that. So we have 26, and then left child is 61, and then left child is 1 and 15 and 48, and the right child is 19 and 5. Okay, so this one is, this element and this element and these elements are kind of sorted. This one is larger than this one, this one is larger than this one. Okay, good. Okay, so this is it. But this is not actually adjust all the tree, right? So we are just focused on this part. Okay, and if you look at this part is not sorted. Okay, so in the next slide, we are going to talk about that issues. Actually, we will not actually call this adjust with unsorted list with 2 and 10. Okay, so we'll talk about that in the next slide. Okay, so this is the heap sort algorithms, and when we call this heap sort, this list is unsorted, and the n is the number of elements in the list. Okay, and since we represent this complete binary tree with an array, so by this one is actually represented by this tree. Do you remember that we could represent a complete binary tree with an array? Okay, so this is an array, and we represent this a binary tree, complete binary tree with that. Now we have two for loops. Okay, first one and second one. And in the first for loop, we are going to adjust the tree, and in the second for loop, we are going to sort. Okay, we are going to delete the maximum element at a time. By doing that, we are going to sort that. Okay, so let's focus on the first for loop. Okay, I start from n over 2. So in this example, I start from 5. Okay, and then we call this adjust function passing list and I and n. So in the previous slide, root is 5 and n is 10. So we focus on this part first and then we adjust. And if you go back to this, so we will meet this part. Okay, root key is larger than the child key in this case. So 61 is larger than 19. And then we break. That's it. Okay, good. And then next, list is the same list and I decreases by 1. So I is 4. Then n is still 10. Okay, so we actually call this adjust function by focusing on this. Okay, I know the n is 10, so this could be involved. Okay, but so when the root is 4, then we will focus on the 4 and 8 and 9, because when we take a child of this 4, then the child is 8. But we have a right child, and right child is larger than left child, so 9 will be child. Okay, and this child 48 is larger than 1, so we are going to swap this one. We copy this one, and then 1 will be restored here. So this one will be 48 and this one will be 1. And then when we go back to the top of the while loop in the previous slide, the child will be 18. 18 is larger than 10, so we stop there. So that's it. So by calling this adjust function passing list and the 4 and the 10, we actually adjusted this subtree. So now look at this one. We have 48 and 15 and 1. This subtree is a max heap, and also this one was a max heap. And now we go back to this one. Okay, by calling adjust function with list and 3 and 10. Okay, then the root is 3, and the 77 is larger than both of the children. Then we stop there, we break. Okay, that's it. Next, we call this adjust function passing the list and 2 and 10. Now we are focusing on this subtree. Okay, remember this one is adjusted and this one is adjusted, and then now we are focusing on the bigger subtree. So we actually compare the two children. So we have a 48 and 61. 61 is larger than 48, then we focus on this one, and 5 is smaller than 61. So 61 will be copied to here. But remember, this one was copied to temp. Okay, and 61 will be here, and now again this 5 is smaller than 19, so 19 will be copied here, and now 5 will be copied here. So we have 61, 19, 5. And then if you look at this subtree, this one is a max heap. Okay, and then this one is max heap, and then next I will be 1. Okay, and n is still 10. So now this one is root. Okay, we do the same thing. So which one is larger? 61 and 77. 77 is larger, and 26 is smaller than 77, so 77 will be copied here, 77. And when we compare 26 to larger child, which is 59, and 59 is larger than 26, so 59 should go up, and finally 26 is here. So this is it. We have a max heap. It's perfect. Okay, so with this first for loop, we adjust complete binary tree to be a max heap. Perfect. And now we are going to focus on the second for loop. But let me summarize the first for loop. So given this unsorted complete binary tree, the first for loop will make a max heap looking like this. Okay, it's beautiful. Okay, and then let's go back to the second for loop. Okay, when we are in the second for loop, it means this list is a max heap. Okay, and here is really brilliant trick. Okay, so I goes from n-1 to 1 by decreasing. Okay, and then by the way, the index starts from 1, okay, not from 0. Okay, so index starts from 1, and I start from n-1. Okay, then we're gonna swap the first element with the last element. Okay, so for the first iteration, I is in this tree, I is n is 10. Okay, and I is 9. Okay, then in the first iterations we are going to swap the first element and the last element. You see that? So I is 9, so I plus 1 is 10. So list 10 is the last element and list 1 is the first element. And by the way, the list 1 is the root node, which is the largest element. And we actually swap the largest element with the last element. So now, after this swap, the largest element is here at the last node. Okay, then the next step, we are going to call this adjust function one more time again, but the indexes are different. The root is 1, okay, and then I is 9. What are we doing here? So we just swap. So let me use this figure. So we just swapped. So now 5 is here and 77 is here. Okay, and then we called adjust function passing 1 and 9. So it means we focus on this subtree. Okay, and 77 is already sorted, and then we are going to adjust this complete binary tree to be a max heap. Then we actually compare this one to children, and 61 is larger than 5, so 61 is here. Okay, and then 48 is larger than 5, 48 is here, and 5 is smaller than 15, 15 is here, and 5 is here. So by calling the adjust function, now this one is a max heap again. Okay, and then we go back. Now I is 8. Okay, and then we call this swap function. So which means we are swapping the first one, the root one, with the last one. In this case, list 9. Okay, which means 61 will be here. 61 is here, and this one will be 1. Okay, and then we call this adjust function one more time. But in this case, the indexes are different. 1 is 1 and I is 8. So which means we are adjusting this complete binary tree here. So this is what we are interested in. Okay, so look at this one, 77, 61. 77 is the largest one and 61 is the second largest one. Okay, and then we adjust this complete binary tree. So now, okay, let's try this adjust function one more time. 59 is larger than 48 and larger than 1, so 59 is here, and 26 is larger than 11 and 26 is larger than 1, So 26, and this one is 1. So this one is again a max heap. Beautiful. And 59 is the largest one. And then in the next iteration, what are we going to do? So we are going to swap this one with this one. Okay, then 59 will be here and 5 will be here. And then in the next adjust function, we will focus on this. Okay, so look at this one. 59, 61, 77, these are kind of sorted list. This is how heap sort works. Okay. This is the second for loop. Okay, so let's take a look at this example to explain explain the second loop with this example. So when we are in the second for loop, this is a max heap. Okay, and then we swap the first one with the last one. It's kind of deleting from the max heap. And then, we have this blue bar. So on the left side, we have max heap. On the right side, we have a sorted sublist. So 77 is kind of sorted sublist, and the 5 is in the root node. So now this is not a max heap, but it's just a complete binary tree. So now we adjust. So 61 will be the root node, okay, and then we swap this one and the last one of this max heap. Okay, and then after swapping, we have a sorted sublist, and then this one is not a max heap, and by adjusting, we have a max heap again, and we do the same thing again and again and again. This is it.